Assalamu alaikum warahmatullahi wabarakatuh. Dear students, how are you all? Our today's lecture for Internet Networking course is lecture number 10 with title IP Traffic Engineering. So we are going to discuss this lecture today and we'll see what are the motivations of this lecture, what are the objectives of IP Traffic Engineering, and we'll see what's going on in it. So let's have a quick background of this. Here it says that the internet has quickly evolved into a critical communication infrastructure. So yes, we all know that the internet has changed a lot, and now the internet is supporting significant, very important economic, educational and social activities. So we all know that internet is used for our electronic banking, and online banking, and other economical issues like e-commerce, buying and selling online, and internet is now also used for educational purposes, like we are having online teachings, and distance learning teaching, online exams, so etc. And as well as some social activities, like we are using our internet for entertainment, for Facebook, Twitter, Instagram. So these are all social activities we are using internet for. Okay, so at the same time we need to keep in mind that since internet is used for economic, educational and social activities, so it means the delivery of internet communication services has become very competitive. So it means what? There is a lot of competition going on for these communication services. So, and definitely the end users, we as the end users, our demand is high. So being the end user for the services of these communications, internet communication, our demand is high, and we definitely require high quality of service from the service providers. So when you talk about the service providers, it means the ISPs. It means the companies that provide these services, of course. So again they said the performance optimization of large, so since the delivery of internet communication service has become very competitive, since the competition is too high and the end users require very high services, high quality of service, so it means what? It means the performance optimization, performance optimization of large scale of IP networks, especially public internet backbones. Public internet backbone means the internet that we get from the backbone, that is the core fiber optic cable, have become an important problem. So to optimize the performance of large scale IP networks, especially the backbones, have become a major problem. And of course the network performance requirements are multidimensional. So it is not only single dimensional, it's not one dimensional. So network performance requirements are multidimensional. They are as well as they are complex, and sometimes they are contradictory. Contradictory means they are opposite. And if you do this, this will go bad, and if you go on the right, the left side will become weak. So this is called contradictory. So making traffic engineering problem very challenging. So it means we, in order to do traffic engineering with all these situations, So this traffic engineering is a challenging thing to do. It's not easy. So what are the things that motivate us? And what encourages us to use traffic engineering? It says number one is that the overall cost of operation by more efficient use of bandwidth resources. So it will reduce the overall cost. If we use traffic engineering in our internet or in our networking, so what will this traffic engineering will do? It will reduce the overall cost. It will reduce the cost of what? Of the operations. You know, operation costs a lot when you have a network, a LAN, a WAN, and you need to keep this network running efficiently. If you need to keep this network up all the time, so cost of operation is always high. So in order to reduce the cost of operation, it is good to have traffic engineering. And another thing what is prevent a situation where some parts of the service provider network are overutilized, congested, while other parts remain underutilized. This is also a very important or very encouraging thing that motivates us to use traffic engineering, is that sometimes if we want to go from node A to node B, so there is a path, there are different paths. So what is happening sometimes, that some part of the service provider network are overutilized. So sometimes what is happening, this path is overutilized and this path is less utilized, underutilized. So what will traffic engineering do here? It will make something like equalization. So if this path is utilized, this will also be equally utilized. Both parts of the network will be utilized. So this is something like congestion will be reduced on this side. Yeah. So these are few motivations that will help the network to be engineered well. So let's look into it more and we will understand better. So here it says, as an introduction, the role of traffic engineering is definitely to optimize. We are here to optimize an operational network. The network is operational and it's working good, but we are here to optimize this operational network. How are we going to optimize, make it better, efficient, better, good, and utilize all parts of the network? How are we going to do that? Definitely we are going to apply some traffic engineering. So it says to optimize operational network so that performance requirements are met and at the same time network resources are well utilized. This is our goal. We want the operational network to be optimized and so that performance requirements, whatever is required by the end user, performance requirement by the end users are met. At the same time, network resources are well utilized. So traffic engineering is of course an important component of IP intra-domain operational networks. The networks which are operational in the intra-domain, there is something called inter and another thing is called intra. So there is a difference, inter and intra-domain. So here it says traffic engineering is an essential component of IP intra-domain operational networks, especially if the network is large. Yes, students, we need to keep in mind that traffic engineering will work better, will optimize an operational network if the network is large. Yani for smaller networks, it will not make much difference. It will not make much difference. So our traffic engineering is applied on large scale networks. Okay, traffic engineering addresses medium-term goals. Okay, we need to keep this point in mind as well. What it says exactly, that not long-term but medium-term, addresses medium-term goals of a network and overall behavior of operational network. So it is traffic engineering. Initially we apply for short-term or medium-term. Yes. Yeah. Applied, yeah, addresses medium-term goals of network and overall behavior of operational networks. Now, one thing is traffic engineering, and the other thing is internet traffic engineering. So what is here? What are we discussing here now? Internet traffic engineering. It says this is defined as the aspect of internet network engineering. We are defining, it's defined as internet network engineering, and it's dealing with what? The issues of what? Performance evaluation and performance optimization, two things. So internet network engineering is dealing with the problems of performance evaluation and performance optimization of the operational IP networks. So definitely if we work on the internet traffic engineering, we are working on the problems of the evaluation problems, whether the network is working okay, if the most of the time the network is up or the most of the time the network is down. So we need to evaluate the network performance. And not only the network performance we are evaluating, we need to also evaluate the optimization performance of our operational IP network. So how do we do that? It says definitely we can do that. This is accomplished by addressing traffic oriented performance requirements. Which performance requirements? Traffic oriented, while utilizing network resources economically and reliably. So utilizing means we'll be using network resources economically and reliably. If network resources are utilized economically and reliably, it means we are addressing traffic oriented performance. And also it encompasses the application of technology and scientific principles to the measurement. Yes, what? It encompasses the application of technology and scientific principles to the measurement of categorization, modeling, and control of internet traffic. Yes. In class, the traffic-oriented performance measures include delay variation, packet loss, and throughput. So all these things helps us to categorize, model, and control the internet traffic. So here we need to understand distinctive functions performed by internet traffic engineering. There are some functions that are performed by the traffic engineering, internet traffic engineering. So they are mentioned here in this way, that the control and optimization of routing function, number one thing. The control and optimization of routing function. Number two, to steer traffic through the network in the most effective way. So how do this traffic pass through the network in the most effective way? So this is the second thing. What are we discussing here? The distinctive functions performed by internet traffic engineering. The third thing they are telling us here is the performance of the network as seen by the end users of network services, that is truly paramount, that is truly up high, good. So we need to see the performance of the network as seen by the end users, not as seen by the providers. So if the end users are happy with the services, and if they encourage and they highlight the services, the network services, it means that the performance is good. So what do should the ISPs do here? So they said that the ISPs should therefore enhance the immigrant properties of the network economically. It's not only that technically the network should be good, but economically the network should also be good. If we provide high rate, very expensive network services to the end users, so definitely everybody can do that. What is role of traffic engineering here is providing cheaper services with high performance to the end users. The rate, the services is cheap and the performance is high. So this is what we are trying to achieve here. So what are the optimization aspects of and objectives? So we need to look into it. Here it says the aspects of traffic engineering can be achieved through capacity management and traffic management. So these are two things we need to discuss here. So what are we discussing? We are discussing the optimization aspects and objectives of traffic engineering, internet traffic engineering. So what is capacity management and what is traffic management? So as I said, the capacity manage includes the capacity planning, and routing control, resource management. So these, now how could this be managed? Network resources of particular interest. So we need to keep in mind that the network resources of particular interest include like link bandwidth, and buffer space, computational resources. All these things include in capacity management. So what did I say? The three things. I said the link bandwidth, buffer space, and computational resources. Okay. The second aspect of traffic, the second aspect of traffic engineering, is traffic management. So what is in traffic management we need to do is, number one, the nodal traffic control functions such as traffic conditioning, queue management, scheduling. So these three things, nodal traffic control, traffic conditioning, and queue management, these things we need to focus, and of course scheduling also. And number two, we will have to arbitrate access to the network resources between different packets or between different traffic streams. So what does this exactly means? That we will have to distinguish the difference. We have to treat different packets, or we need to differentiate the different traffic streams differently. High bandwidth traffic, or that packets, that frames, that traffic which needs less delay, and those which can have some delay. So there is a difference between the packets and traffic types. We need to arbitrate the access to the network resources for these two traffic types or these different packets. We'll discuss this in more detail in the coming slides. And another thing we need to keep in mind, that the optimization objectives of internet traffic engineering, we need to look into it continuously. Not at just one time we'll focus on these things and the other time we forget to optimize our traffic, the packets and the network types. So the optimization objects of internet traffic engineering should be viewed as a continuous process of network performance, in order if we want some improvement, and it's not a one-time goal. Okay, So these were the aspects of traffic engineering. Now let's look into what is IP network traffic. So here it says that IP network provides many services. We know that the services that is available on the internet is, for example, like email service, telnet, news groups, yeah, like mailing list, internet telephony, which is also known as voice over IP, and messaging. So all these are the services which is provided on the internet. So it has been reported, it says here, it has been reported that on a backbone link approximately 90% of the traffic is TCP based. So it means 90% of the traffic is TCP based, means connection oriented traffic, yeah, reliable traffic. So all these types of traffic is available on the backbone. So in other words, now traffic in an IP network is IP datagrams generated by various applications. So definitely different type of applications like email service, telnet service, news groups, mailing list, all these services are generating the datagrams. Definitely various applications means different type of applications. Without wondering which among the application it is for. So it is free datagrams are generated, they are in the network, they are in the internet, and they have to reach the destination network. So what are the number of IP packets flowing on a link in a certain unit of time? So how do we measure the number of packets? So this is the question. The number of packet flowing on a link in a certain unit of time. So how do we measure that? They said we can measure them in PPS, that is called packets per second. Time unit is considered in seconds. Thus traffic volume can be specified in terms of IP packets offered per second, or we call it packets per second, PPS. So another measure of traffic volume that is often used, that is for raw data. That raw data rate units such as megabits per second, we also write it as Mbps or Gbps. So students, we need to keep in mind here that if it is the traffic volume can be specified in terms of packets, and the traffic volume can be specified in terms of raw data. So if it is specified in terms of IP packets, it will be counted as PPS, and if it is measured, traffic volume is measured in the form of raw data, so that would be measured in megabits per second or gigabits per second. Yeah. How do you measure what you call the traffic and performance? To measure the traffic and performance, for that, so in that case, delay is a critical performance parameter. Since we are interested in ensuring that a packet generated from one end reaches the other end as soon as possible, yani sender to the receiver, the packet sent till it reaches the receiver. So what we want is it has to reach on the other end as soon as possible with a minimum delay. So in our case, they said in order to measure the traffic and its performance, delay is a critical parameter. So we need to keep in mind that what is the role of delay in sending the packet, while sending the packet from the source to the destination. So here they are telling us an analogy. What analogy? This analogy is between the road transport network, the road transport where the cars are moving on the roads, highways, and the IP networks. So what is the similarity? The analogy here is telling us that in the road transportation, in the road highways, delay of traffic, delay of cars, how slow the car will reach from, for example, from Ibri to Muscat, how slow or in what time it will reach, or what is the delay between the highway, in the highway, it depends on the volume of the cars as well as the number of lanes. So it's very clear what is the analogy between the IP networks and the road transportation is. In road transportation, it depends on the, for example, this is my highway, I have 2 lanes and the number of cars. So if the number of lanes are 2 and the cars traveling on the road are more, so definitely delay will be high. Delay will be high. And if we add another lane here on the highway, so you can see that this congestion will be less. Some of the traffic from here will be shifted to this way, and this traffic will be shifted here. So in this case, delay will be less, and the delay will be less, and of course the vehicles will reach to the destination faster and earlier. Similarly, this is happening in IP networks. If the number of channels from the source to destination are more, and definitely the frames are less, the packets are less, so it means the delay in the network, IP network, will be less. So this is what they are telling us, giving us an example of analogy between road transportation and IP networks. Now let's look into some models which will help us understand this traffic engineering, implementation of traffic engineering. Here they are telling us implementation of traffic engineering with layer 2 overlay model. So what is this overlay model? Overlay model actually is a virtual circuit network, such as like ATM, frame relay, or WDM. So these provides the virtual circuit connectivity between routers that are located, between the routers that are located at the edge of the virtual circuit cloud. So here they are telling us this is the physical view of layer 2 physical view, and then this is the logical view. Let's read this. It says the use of explicit layer 2 transit layer. The use of explicit layer 2 transit layer allows very exact control of how traffic uses the available bandwidth. So this layer 2 explicit control of layer 2, these are the routers. So it shows us, it allows the exact control of how traffic uses the available bandwidth. And this logical diagram is telling us layer 3 at the edges. So this one is the inner one, and when you look to the outer network, layer 3, it will show this way. So this is what a complete mesh. Here it is not showing us the mesh, but here logical view is showing us the mesh topology. So each router is connected to the other router when you talk in about layer 3. In the fully meshed overlay model, each router would pair to every other router. in the network, so that the total number of adjacencies is a quadratic function. Yeah, so that the total number of adjacencies is a quadratic function of the number of routers. So we will discuss this in the next slides and we'll look into it. So in this slide, let's look at the diagram. The diagram is telling us that the router R1, R2 are the senders, is the source, and they are traveling through the network. So in this model, they are telling us the traffic engineering layer 2 using the overlay model allows for detailed decisions regarding which link should be used to carry different traffic patterns. So what traffic patterns we have? We have a red traffic pattern and we have a black traffic pattern. So if you see here, R2, R3, the edge routers, edge are the routers, and in the middle we have these switches. These are called multi-layer switches. These are not layer 2 switches, but in fact these are layer 3 switches. So these signs are telling us that these are layer 3 switches, multi-layer switches. So what we see here, the PVC for R2 to R3, the PVC from R2 to R3 is red color traffic, and the PVC for R1 to R3, this one is black color traffic, and this is red color traffic, R2 to R3. So let's understand. It says from R2 to R3 uses a PVC which takes the shortest path using the upper transit switch. So what is the shortest path in this scenario? The shortest path, of course, is R2 to R3 via the red color path. So how many hops? It's one router, one switch, multi-layer switch in between. So definitely any traffic that is coming will prefer this route to R3 and will ignore this path to R3. Why? In this case we have 3 multi-layer switches, or you can say we have 4 multi-layer switches, 1, 2, 3, 4, and in this scenario we have 1, 2 and 3 switches. So most of the traffic will prefer using this path. So this is what it says here. Traffic engineering in layer 2 using the overlay model allows for detailed decisions regarding which link should be used to carry different traffic patterns. So from R2 to R3 uses PVC which takes shortest path. Which one is the shortest path? As I told you before, this is the shortest path. Traffic from R1 to R3 uses PVC which does not take the shortest path. So what is traffic engineering doing here on layer 2 is applied to let the PVC uses links that would otherwise have been underutilized. And if we did not apply traffic engineering here, in this scenario, if we did not apply traffic engineering, so all the traffic would prefer using R2 to R3 red side. So after applying traffic engineering in this scenario, we forced the traffic, the PVC black color traffic, for example, to use R1 to R3, and the red color we forced it to use R2 to R3. If we did not apply traffic engineering, this side of the network would have been underutilized, and this one would have been overutilized. So traffic from R1 to R2 is using this one. Traffic engineering on layer 2 is applied to let the PVC uses link that would otherwise have been underutilized, and the upper path would have been overutilized. So let's look into some drawbacks of overlay solution. For example, the first drawback of overlay solution could be extra network devices. Since we are providing two different paths, upper path and lower path from source to the destination, so we are using extra extra devices, like in this case. So these are a lot of devices used: R2 routers, R1 routers, R3 routers, layer switches, multi-layer switches. So extra devices, of course. So this is one of the drawback. And another drawback could be more complex network management. When there are more devices and then you are applying traffic engineering in it, so it means that there is some complex network management involved. So two-level network without integrated network management, upper level, lower level, multi-layer switches, and the routers. So it means we have two levels of networks without single network management. And the staff that is going to support this operational network, we need additional training, technical support, field engineering. All these things will be involved to keep the network running up and smooth. And other than that, we have the routing protocols, interior gateway protocols, routing, scalability issues for mesh topologies. Definitely for layer 3, we said it's a complete mesh, so we need IGP routing scalability. Sometimes we need to make sure that it is scalable. Other drawbacks could be additional bandwidth, overhead, no differential service, class of service, and so forth. So let's look at some questions related to overlay solution. It says, what are the drawbacks of using overlay networks? So definitely we have looked into some drawbacks. Some of the drawbacks are like two-level network, additional training. This comes into more complex network management. Another drawback is, like, for example, extra network devices and IGP routing scalability issues for mesh. So these are some of the drawbacks which we can write in different words. Like, for example, the layer 2 devices do not have any layer 3 knowledge. Of course, the layer 2 devices, the multi-layer switches which are inside, they do not have the knowledge of the routers which are outside. So these devices which are inside, they do not have the knowledge of the devices which are outside. Something like this. So these are routers, R1, R2, R3. So the switches inside, they do not have the knowledge of layer 3 routers outside. Network must be knowledge of intelligent queuing and dropping. The layer 2 and layer 3 network must be highly meshed. This is a drawback. They are highly meshed and connected to each other. As we saw, I'm not able to draw it very well. Let's look into the previous diagram that is already there. This one. So this one is highly meshed. And in this scenario, layer 2 devices are not aware of the layer 3 devices which are outside. So these are the same drawbacks that we have learned in the previous slide, but in different words. Two networks must be managed. As I said before, two-level network. Layer 2 and layer 3 must be fully meshed. So some of them are in different words only. Okay, let's look into implementing traffic engineering with layer 3. Earlier we discussed implementing traffic engineering with layer 2 model. This is with layer 3 model. With layer 2 model means that those multi-layer switches were involved. In this case, it's not multi-layer switches, it's of course layer 3 switches, layer 3 routers. So what it says here, it says if the same network topology is created using routers, layer 3 devices, traffic engineering must be performed differently. Now if you look at the scenario, we have R1, R2, R3, R4 and R5. So how many routers from source to destination? We have 3 hops. Yeah, any 3 routers we have in between. 1, 2, 3, and then we reach at the fourth hop. So 3 routers in between. 1, 2, 3. And if we look at the other way downwards, we have one router R6 and R7 only. In this case R2, R3, R4, and the other way we have R6 and R7 only. So the dashed arrow, okay, if IP mostly uses destination based least cost routing. Yeah, destination, IP is using mostly destination based least cost. So in this scenario, what is the least cost? The least cost is the less number of routers. The less number of routers is the least cost. So the less number of routers are of course this way, and the more number of routers are this way. The dashed arrow denotes an underutilized alternative path. So this path is underutilized and this path is overutilized before applying traffic engineering. Yes, class? So I hope the students are with me. They are able to understand what I am telling them. And if you have questions, please do not shy to ask your respective teachers, your respective college, university teachers. Okay. So if the same network topology is created using routers layer 3, we have to apply traffic engineering differently. It says if no traffic engineering is applied to this network, traffic from both R8 and R1 towards R5 will use the least cost path, which is the upper path, least cost path, which is the upper path. So this flow may result in the overutilization of the path R2, R3, 4, 5. So this path will be overutilized. Why? There is no traffic engineering. We are not forcing any kind of traffic to use this path. We are not forcing. So until we apply traffic engineering, that is, we force the packets to travel through R2, R6, R7. If we will not force them, they will use the least cost path, and this network will be overutilized. The flow may result in the overutilization of the path R2, R3, R4, R5, while the path R2, 6, 7, 4, 5 is underutilized. Yeah, the path R2, 6, 7, 4, 5 is underutilized. This will be less utilized. This is what they are telling us. So, a routing solution to traffic engineering. Here it says that the current forwarding paradigm centered around destination based. Yes, the current forwarding paradigm means the current forwarding paradigm which is based on what? Destination, is destination based. Yani we need to reach the destination with least cost. So it says that this is inadequate, or you can say insufficient. Yeah, is not enough. So path computation based just on IGP metric is not enough. Yani we are computing the path computation based on IGP metrics. IGP metrics is one of the IGP metrics could be less hops, less number of hops. So it says this type of computation of path is not enough. Another point, it says support for explicit routing, source routing is not available. Yeah, since we are not providing explicit routing, yani we are not forcing the packets to travel through the alternative path, this is also not available. So supported workarounds, static routes, policy routing. Yeah, so these are all what do you call these are all alternatives or the ways in which we can provide routing solution to traffic engineering. It could be in the way that they said, since it is not enough, IGP based metric is not enough, and you are not supporting explicit routing, is not available, and static routes and policy routing is not there. So they said that you need to find solutions to trafficking. This could be the solutions. Yeah. So let's see. Here it says check yourself. There is a question saying that why does traditional IP packet forwarding not distribute the load over all links? And why do you have to use traffic engineering here? Or why doesn't the traditional IP packet forwarding mechanism cannot distribute the load of traffic over all links? So the answer could be in different ways. It says in A it says it can, but it requires special switching code. And you have to use a special switching code to distribute the traffic over other links. Then it says in B, the IGP makes one decision. Yani the interior gateway protocol, whatever you're using, RIP, IGRP, whatever. The interior gateway protocol makes one decision as to how to reach any destination. Yani from source to destination, the IGP is making one decision, is how to reach the destination. So with the exception of load balancing, IGP does not care of load balancing, does not care about load balancing over equal paths. So alternative routes with higher metric are not used. IGP definitely it will follow its own matrix. IGP follows its matrix. And one of the metric, as I said earlier, is least cost, less number of hops. So why will it use in order to balance the load balancing? IGP will not care about load balancing. This is number 2 point, that why doesn't traditional IP packets forward distribute the load over all links. Number 3 point could be the IGP will always make only one decision as to how to reach any destination, then all traffic towards that destination follows the same route. So once an IGP makes a route from source to destination, other than all the traffic towards the same destination will follow the same route. It will not think of using other route. Once IGP has developed this route, then it will not, other traffic that is coming will follow the same route. To the destination follows that route. Other point could be all routes are used and forwarding is proportional to the total cost. It says that all routes are used and forwarding is proportional to the total cost. We need to make sure that the total cost is directly proportional to the routes used. Yeah. So these are few points we need to keep in mind about why doesn't this traditional IP packet forward not distribute the load over all links. Okay students, in this slide this topic is telling us that MPLS, using MPLS to implement traffic engineering. Yani we are implementing traffic engineering on layer 2 on, just hold on, we are using so as I told you that we earlier implemented traffic engineering on layer 2 and layer 3. So here they are telling us that how to use MPLS to implement traffic engineering. So in short we write it MPLS TE. So in the previous lecture, if you remember, lecture 9 was about multi-protocol level switching. Multi-protocol level switching. So in that lecture we discussed that how MPLS network is compared to a conventional network, and how in MPLS network we use tags, ingress traffic, egress traffic, if you remember all that. So they said that the idea of MPLS TE, yani multi-protocol level switching, traffic engineering is based on multi-protocol level switching that integrates. Yani MPLS TE is based on MPLS, which MPLS? That integrates a level swapping framework with network layer routing. So it is the integration of label swapping with network layer routing. So what happens in this case, it says when you implement MPLS in traffic engineering, it says packets at the ingress are assigned labels. Like in any MPLS networks, any packet that enters from a conventional network to a MPLS network, so at the ingress labels are assigned to the packets. So are assigned labels through tag distribution protocols. Which protocol is used? TDP, or we call it LDP. So these two protocols are used to assign labels to any packet that enters the MPLS network. It says here also the BGP, Border Gateway Protocol for Virtual Private Networks. In that case, in that scenario also, TDP and LDP are used to assign labels. What are these labels doing here? In this case, labels represent the path through the system. That is the LSP. So each label represents the path, yani through what path the packet will travel, will be switched. Through what path the packet will be switched. So that is label is representing the path, the LSP, label switching path. Forwarding within the MPLS network is based on labels. Yani in short, what are we doing here? We are integrating MPLS with network layer routing. So this is what we call, in short, that we are using MPLS to implement traffic engineering. Yes, students. So how do we forwarding in MPLS traffic engineering? How is it forwarding done? They said that forwarding is based on explicit MPLS LSP. Explicitly. Yes, it says it's done on explicit MPLS LSPs. Means MPLS traffic engineering provides benefits similar to the overlay model. Yani the benefits are similar to the overlay model. MPLS and overlay model benefits are similar, but without these 3 points. What are the 3 points? We know that in overlay model we have a separate layer 2 network. We have non-scalable full mesh of routers. Non-scalable full mesh of routers. That is virtual circuiting, we said, in layer 3 routers. Yeah, fully meshed. So this was there, but in MPLS this is not available. Non-scalable full mesh of routers. Interconnections are not there in MPLS-TE. Otherwise, the benefits are similar. Okay. IP mechanisms for traffic engineering says here that circuit style forwarding, that is known as MPLS. We use signaling, resource reservation protocol. This is also used. Circuit style forwarding is the other name is MPLS, and it's also known as MPLS. So these are what IP mechanisms, different mechanisms. So these are different IP mechanisms, mechanisms for traffic engineering. Yeah. So one of the mechanism is circuit style forwarding. As I said, circuit style forwarding is also known as MPLS, multi-protocol label switching, in which tags are involved. Yeah, ingress, egress routers are involved, and all those things which we discussed in the previous lecture. The other mechanism for traffic engineering, IP mechanism, is RSVP, known as signaling also, resource reservation protocol. RSVP is a soft state signaling protocol. Yeah, it supports receiver initiated establishment of resource reservation for both multicast and unicast flows. So it was developed by signaling protocol within the integrated service of framework. So this is about RSVP. The next is constraint based routing. Yeah, constraint based routing. Extended intermediate system to intermediate system, that is, you can say, instead of writing or reading ISIS, yani this one, we just we normally use it with the name ISIS or OSPF. So these are the constraint based routing protocols we use here. That, as I said, we use it with a short form as ISIS or OSPF. So what is exactly this name says? Constraint based routing. Constraint based routing refers to a class of routing systems, yeah, to compute routes. So it is used to compute routes through a network subject to the satisfaction of what? Of a set of constraints and requirements. Any set of constraints and requirements. So it will compute the routes. Compute routes. So constraint based routing, compute routes. So how do you compute the routes? In other words, we use these protocols, link state protocols, that is short form is ISIS or OSPF. Then another mechanism, IP mechanism for traffic engineering is routing onto tunnels. Yani we route packets onto tunnels. So we call it extended also, tunnel aware. What protocols are used? ISIS, OSPF, shortest path first algorithms. Then forwarding is also used. In forwarding mechanism, this is also traffic engineering, IP mechanism for traffic engineering. Installation of tunnels in the, yes, we installed tunnels into the FIB, forwarding information base. So these are few IP mechanisms for traffic engineering. Here comes another question. It says, what does MPLS provides that allow for traffic engineering? So the answer could be the separation of forwarding and switching decisions, separate of routing table containing. So if you read them, they are very clear, all the 4 points. So students, this was our lecture number 10. So this was about IP traffic engineering. We discussed few things. I would like you to go through this lecture very well and ask questions from your respective university campus teachers, your instructors, and hopefully it will be beneficial to you all. Thank you very much for attending this lecture. Take care of yourself. Bye.